how to drive the equation for the pressure in the gases, right?
Yes.
So that is the concept of the ideal gases. And there is one more chapter related to the thermal.
Thermodynamics. Yes.
Yes, so today we have to start with the concept of thermodynamics. Okay, so basically we have to start with the concept of thermodynamics. And in thermodynamics, first of all, we have to start with the concept of the energy, because in the last topic, if you remember, we discussed there is a concept of macroscopic and microscopic. So now we have to discuss about the microscopic concept. And in microscopic concept, you know that there is a concept of kinetic energy, the internal energy, the potential energy. So basically, if we want to talk about the concept of the microscopic property, so in microscopic property, there is a concept of internal energy. So basically, internal energy is very simple concept in internal energy. If they ask about internal energy, so internal energy is the sum of kinetic energy plus potential energy, right? So if they ask about what is internal energy, so simply we can say that because in gases there are different energy involved over there, so we are not sure that what type of energy actually act over there. So that's why we use the concept of internal energy. So internal energy just sum of all the concept, like it is the sum of internal sum of kinetic plus potential. So in this chapter, mostly we are going to use the concept of internal energy, right? And the symbol for internal energy will be small u. And again, you know the SI unit of energy is joules. So same unit for the internal energy concept, right? Any concept? Any confusion over here?
No.
Okay. So basically, this internal energy actually relates with it is related with temperature, because when we increase the temperature, so the kinetic energy of molecule will increase and it will start to vibrate, it will start to collide with the walls of the container. So basically temperature or the thermal source is the basic source of the internal energy that will increase or decrease the internal energy of the system, right? So when any gas container is heated up, so molecules begins to move faster around in the container, so their kinetic energy will increase. And if we are talking about the solid, so in solid, you know that molecules are only able to vibrate about their fixed point. Okay, so in the last chapter we already drive the equation for energy, that is also same for the internal energy. You remember that equation, kinetic energy is directly proportional to temperature.
Yes.
So basically we drive that formula, and that formula will give you the concept of the internal energy, right? कुछ खाए? So basically in equation number 1, internal energy, just like the same formula of kinetic energy, it is equals to 3 over 2 k into t. And again, if you take the value 3 over 2 k as a constant, so your internal energy is directly proportional to temperature, right? By using this equation, you can simply identify that energy is also directly proportional to temperature, right? And we already discussed the concept of pressure last time, so we are not going to discuss that again and again, because you got the concept that how this situation works for temperature and energy. Okay. And the second thing, which is related with the energy, because you know that whenever we talk about the concept of energy, so there will be a concept of work done also, right? So if we talk about the work done by a gas, work done by a gas means when force is applied on the wall of container and displacement is covered by the molecules. So work done is equals to a force into displacement. But in this concept, we are talking about with the concept of pressure and volume. So basically your work done is equals to pressure times volume, and we are also going to drive that how work done is equals to pressure into volume. So for that purpose, let's suppose if we first consider the first law of thermodynamics. So this is the most important topic in this chapter. First law of thermodynamics. So basically in first law of thermodynamics, let's suppose if we consider a container. Okay, so we are having container right here. And in this container, let's suppose initially your piston is placed over here. So basically this is the piston which you are able to move in upward or downward direction. And you can see there is a certain level of volume of gas filled in it. This is the volume. And let's suppose if it starts to apply the thermal energy, or if it starts to supply the thermal energy to the container, delta Q is the amount of energy that we are going to provide this gas, and piston is free to move. So what actually happens when we supply this energy? So basically your piston starts to move in upward direction, right?
Yes.
So it will move in upward direction, and your new level of piston will be somewhere, let's suppose, over here. And we can see that your volume increases with the help of the thermal energy, because we already discussed that with the help of temperature, the internal energy increases. So in internal energy, we are actually talking about the kinetic energy. So due to that increase in kinetic energy, your volume will starts to increase. And if we compare the level of the volume, so initially we are at this level, and finally we are at this level, right? So let's suppose the initial level of the volume is, let's suppose, V1, and the final is V2. And there is a change in the displacement of the piston. This is the change in the position of the piston, right? Clear? Any confusion?
No.
So basically, this is a very general, very common, very simple process. So basically, the first law of thermodynamics states that we have to state the law with the help of this experiment. So the first law of thermodynamics states that the increase in internal energy is equals to the, basically you supply thermal energy. That thermal energy helps to move the piston. It means to do the work done, plus your internal energy of the molecules also increase. So this is a very basic first law of thermodynamics, that your thermal energy actually utilize into a useful work done, plus the increase of internal energy. Okay.
Okay.
So your increase in internal energy is equals to the energy supplied by heating plus work done on the system. So this is the basic definition. And if you want to write the equation, so equation is also very simple. We know that internal energy represents by symbol U. Increase in energy is equals to the thermal energy supplied, that Q, plus the work done, that W. So this is the equation of first law of thermodynamics, very simple equation. Clear?
Yes.
And you know that the SI unit of energy is joule. Again, the thermal energy is type of energy, so that is also joule. Plus the work done is also, the SI unit of work done is also joules. So all quantities having SI unit of joules, right? In this equation. And there is one more important thing. Uh, let's suppose if you are going to supply the thermal energy to the system, like to the container, and there is another way that we are taking thermal energy from the system, like from the container. So there are two possibilities, right? And before that, if we just continue with the equation of work done, so basically work done is equals to Force into displacement, right?
Yes.
And we know that in this concept, let's suppose displacement is delta x, because the change in position shows you the displacement. And if we talk about the force, so what type of force we are using? We are using the force with respect to the pressure. Pressure is equals to force upon area, right? So we have to use that concept. So force is equals to, because we know the basic formula. What is the basic formula? Pressure is equals to force upon area, and force is equals to pressure times area. So we have to use this value of F in the equation. So your equation will be equals to Q plus PA delta X. And again, you know that if we combine A and delta X, so that will make a complete volume. So your final equation will be, right? So this is the final equation. So if they ask you to drive the equation for the work done, so these three steps will help you to drive the value of the work done. So basically work done is equals to pressure times change in volume. Okay.
Yeah.
And one more thing that we are talking about, the positive and the negative sign. What is the concept of that? We also have to discuss that one. So let's suppose if we first talk about the sign of internal energy. So the sign of internal energy will be, if we are using positive sign, so positive sign means that your internal energy increases. Like in your question, if they ask that internal energy increases or internal energy will increase, so it means you have to use positive sign with U, right? Further, if they ask about the thermal source or the heat energy, so basically when we are using positive sign with U, so it means that heat is added to the system, just like in the example we discussed. And the third thing is work is done on the system. On the system means by a gas, right? In simple words, by a gas, because you know that gas actually push that piston. So if you find these terms in your question, so you can easily identify that which sign you have to put with your value in the question, right? And let's suppose if values are not like the same given in the situation, so we have to use the negative sign. And what is the concept of negative sign? The first thing is that your internal energy decreases. So when your internal energy decreases, you need to use the minus sign. Second, heat is taken away from the system. So now you have to write all the opposite point as compared to the first point, right? And third means work is done by the system. It means on a gas, right? By the system means on a gas. Clear? Any confusion?
No.
Okay. So basically, we can say that one more thing. When gas expands, just like in the example we already discussed in first law of thermodynamics, so your work done will be negative. And when your gas is compressed, so your work done will be positive. These are very basic and important points because your formula is very simple already. So you just need to know about these things because that will change your complete calculation for the formula. And this is the concept, right? So like
Yeah.
when the gas is actually compressing, in this situation, your work done is negative, right? Because gas is expanding. When gas actually presses down, so it means work done will be positive. Okay. And let's suppose if we further continue with the first law of thermodynamics. So let's suppose if we consider two possibilities. You remember the concept of Boyle's law and Charles' law, right? In one situation, we just keep the pressure constant, and if we take the volume constant. So let's suppose if we work with two different concepts, like if we take pressure constant one time and if we take volume constant one time, so what will be the graphical representation? Let's see that. That is known as the PV diagram or the PV graph. So next topic is related to PV diagram or PV graph. PV means the pressure and the volume, right? So let's suppose if we take two examples. In the first one, we have to discuss constant pressure. So let's suppose if we want to draw a graphical representation for constant pressure, we are having y-axis, we are having x-axis. So let's suppose if we take volume on x-axis, pressure on y-axis, right? And any random point we select, let's suppose this is your initial volume and this is your final volume, right? And you know that your pressure is constant. So if we take any random value of the pressure, so your graphical representation will be at V1 your pressure will be this, at V2 your pressure will be again same. So you are getting a straight line like this. Okay. And the area under this graph actually shows you the work done. Okay. And let's suppose if you take the constant volume example, so your graphical representation will be different. If we take the example of constant volume, again, we just mark the X and Y axis. This is V, this is P. And now we are taking any random value of volume. So volume is constant. This is the volume. And now pressure is variable. So this is pressure 1. This is final pressure. So the value that is actually changing over here, this is our initial value. And this is the final value. So your graph actually moves in upward direction, right?
Yes.
So basically, they will ask about the graphical representation also in exam. So it is important to know about the graph of the constant pressure and constant volume, and that is very simple, right? Very basic.
Yes.
So basically, your work is only done when volume changes, right? Because in constant volume, volume is not changing, and when volume does not change, so there will be no work done, right? Because in work done, we have to displace the things, and when there is no displacement, so there will be no work done. Okay,
Yes.
so work is only done when the volume of a gas changes. So this is the concept of PV graph, or pressure volume graph, or pressure value volume quantities, right? And if they ask about work done by the gas, so we already defined the formula that work done is actually equals to force into displacement. And if we replace this F with this formula, and we replace it with delta X, so your work done actually equals to and this is actually 3 times the length, area into length. There are 3 lengths combined in this concept, so we can simply say that this shows you the concept of volume, right? So this will be your derivation of work done, right? Okay, last time we discussed the concept of the ideal gases, and now today we discuss about the concept of thermodynamics, right? Now we have to solve some questions
Yes.
related to the thermal section, because I also told you that there is one more chapter that is related to the temperature, but in that there are basic concepts related to your IGCSE, so that is not much very difficult. You will find that question during the, or that concept during the questions when we are solving this concepts. So let's suppose if we start with the concept or with the questions related to the thermal section. So let's suppose if we start with the very first question. So in first question they are asking, state the basic assumptions of a kinetic theory of gases. You remember
Yeah,
that
yes.
we write different points related to the basic assumptions of the kinetic theory of gases, right? That they are in random
Yes.
motion, and we discuss around 5 or 6 points. Okay, so you just need
Yes.
to write those points from your notes, because we already discussed that much in detail. So I'm going to write that again because that is just a copy paste question, right? And you can see that is for 4 marks, like a free 4 marks for your question. Okay, next question is using equation of for the pressure of an ideal gas to deduce that the average translational energy. Okay, okay. So basically, in simple words, what they are asking, if you remember, right? So this is the equation that we discuss. And if you remember that derivation, let me show you. Yes, we define in the next section. If you remember, we started for the derivation of pressure, and from that derivation, I told you that there is a concept of kinetic energy is directly proportional to displacement. So we also need to solve that concept, right? So uh, just advance that derivation and another concept. Uh, yes, this is the derivation, right? So this is the question: kinetic energy is directly proportional to the temperature. So they are asking the same thing, right? So you need to follow this all derivation to again drive this relation, right? Like in short, if I just write that we have to take the reference from equation that PV is equals to 1 over 3 Nm root mean square speed, and PV is equals to nRT, or you can also use the equation PV is equals to nKT. It's up to you. So these are two equation, and when we compare these equation, so on one side we just write T, and on second side we just write, right? You can see we did the same thing, NKT, right? We use NKT and 1 over 3 NMC square. So we are doing the same thing, right? We can also use with the concept of nRT. And this is small n actually equals to the total number of molecules divided by Avogadro number, right? So we can substitute this value in the equation, and we'll cancel out the n on the other side, and we will get this one. And one more thing, that R over NA is equals to the Boltzmann constant, right? So we just replace this value with the K. So your equation will more simplified. And finally, if you remember, in kinetic energy, there is a value of half mv square. So we just forcefully multiply and divide value to in the equation to get the value of half mv square, right? So multiply and divide equation by 2. So finally, you will get the same equation like this. Okay?
Okay.
Any confusion?
No.
Okay. Okay, this is related to nuclear fission or fusion. We will further.
Wait, sir. Sorry.
Hmm?
Can you clarify what will we do after this KT? We will
Oh,
multiply by 2.
Okay, basically, you just multiply one side, multiply and divide by 2. So this is the step that we are working on. KT on the left side and 1 over 3 MC square. So you know that we just multiply and divide by 2. We just shift 3 and 2 on the left hand side. So it will be 3 KT over 2. Okay.
But sir, is there any specific reason why would we
Uh,
multiply by
basic,
2?
Basically, this is the derivation part. It is already derived. We just need to know the steps that how we drive this formula, because formula is in front of you. So with the help of this formula, you just need to
Yes.
drive that same equation, right? So that's why we are just using the same
Yes.
concept,
Okay.
same derivation, because these are the derived fixed values, right? Okay.
Okay.
And the next part is related to the nuclear reaction. That is the last chapter. We will skip that one for the time being. And let's suppose if we consider question number 2, an ideal gas occupies a container of volume. This is the volume at pressure. This is the pressure and temperature. This is the temperature. Show that the number of atom of gas in the container is. So you just need to show the number of atoms, right? Basically, answer is given. You just need to use the calculation and you need to show that your number of atoms is equals to this value, right? And you remember that we discussed small n is equals to number of molecules divided by Avogadro number, right? So basically, if we start with the same concept, PV is equals to NKT or PV is equals to nRT, right? So any one equation you choose. So let's suppose if you write PV is equals to nRT, right? So pressure, volume is given, temperature is also given. R is a constant value and small n is not required. We have to find the capital N. So PV is equals to N over NA to RT, right? Now we are actually finding the value of capital N. So this will be your final equation, right? So pressure is equals to this, volume is, and Avogadro number is a constant value, right? So P, V, and A, this is the value of these three value terms divided by R. R is also a constant value. These all constant value will be given in your data table as you already know in AS, just like temperature is 20 Kelvin. So multiplying divide all the thing, you will get your final answer. That will be equals to 2.8 exponent 23, right?
Okay.
Any confusion?
No.
Okay. Basically, this chapter is slightly easy in the sense of solving the question, because mostly questions are just like straightforward. Like in next question, they are asking atoms of a real gas each have a diameter of 1.2 exponent minus 10 meter. So diameter is given. Estimate the volume occupied by this number of atom of the gas. So now number of atoms is given this time. Okay. So how you solve the concept or how you find the volume? Any idea?
We will use the same equation.
Basically, if we use the same equation, so value of d, that is diameter, we are not able to use that value in the question, right? Because there is no link of diameter in the equation. So basically, they are asking estimate the volume occupied by 2.8 into 10 to the power 23 number of molecules or number of atoms of this gas. So basically, what we need to do, if you consider that we are using a container and container, the volume of a container is given. So let's suppose if we use the concept of the volume, so the volume of the container will be given by 4 over 3 pi r cube, right? So that will help you to find out the final answer, right?
Yes.
So this equation will help you to find out your final answer. So by using this equation, you can easily identify the final equation.
So R will be,
The
we will
times
use
of the diameter.
diameter.
Yes, you have to use the same value and just multiply with the value of n, like we just write the values. And normally we consider for one atom or one molecule, but they are asking about the given number of molecules. So you just need to write original value multiply by the total number of molecules. Okay,
Okay.
so that will give you the complete volume. So this is the concept, right? And further, if you observe the question, and in this part they are asking, by reference to your answer in part 1, suggest whether the real gas does approximate to an ideal gas. So basically in second part they are asking the first part, the answer in the first part, which is equals to this value. In first part they are asking the number of atoms. So question is, if we take the number of atoms given in part 1, or we calculate the volume over here in this part. So the volume calculated in part 1, so we have to suggest whether the real gas does approximate to an ideal gas. So basically they are asking the volume we calculated is approximately equal to the volume of an ideal gas or not. So they are asking the thing. So after calculating the value, if your value is close to the volume of the ideal gas, right? So then we are able to write that yes, it is close to the real ideal gas equation. Otherwise, we are not going to write the same thing, right? And in the same way, you will find the same questions like question number 4. Explain qualitatively how molecular movement causes the pressure exerted by the gas. If you remember in your IGCSE, they will ask the question like this, right? When you just apply the heat energy or the thermal energy, so the kinetic energy will increase and they will start to hit the wall of the container more frequently, and that will increase the force on the walls. It means the pressure on the walls will increase, right? And in part B, the density of the neon gas at a temperature of 273 Kelvin. This is the temperature, and the pressure. This is the value of pressure. Is this is the value of pressure, and kilogram per meter cube is the density. Neon may be assumed to be an ideal gas. Okay, calculate the root mean square speed of neon atoms at 273 Kelvin. So we know that with the help of pressure, the equation that we drive, it is equals to 1 over 3 times density into root mean square speed, right? So pressure is given, okay? The value of pressure is given. One over three. Density is, and we have to find this value. Okay, now so you can see that question is very much simple. Okay, you just need to multiply 3 over there, divide by 0.9, so you will get the answer of root mean square, and just taking the under root, so that will be the final answer of C. Okay,
Okay.
and in second part they are asking 546 Kelvin. So the initial temperature is 273. So basically in second part your temperature actually doubles, right? So the temperature in the second part is actually double. So you know that your energy or your speed is directly proportional to the temperature. So it means you just need to multiply the given speed. Let's suppose if you get any value in over here, if you just find out the final answer. So the final answer of this speed will be equals to the speed at the 273 given temperature, right? So let's suppose if we just double the temperature, so you know that your speed will also increase, right? So you just need to multiply the value by 2, and before that if you just write the value of C square, so this is the value before taking under root, and according to the temperature, according to the equation, root mean square is directly proportional to the temperature. So your temperature is doubled, so it means that multiply by 2 the calculated value. Okay, so then you will get your final answer. Clear?
Yes.
So basically in this chapter you mostly found question related to the general gas equation, PV is equals to nRT, and some questions related to the temperature and pressure. Okay,
Okay.